At this point, I think we've got a fundamental set of equations that we can talk about, get a few solutions, look at. But as is always the case with an illustrative example, you should do better if you go in a quiet room, look at it, think about it, and see what physically the problem's all about. So for that reason, I'm going to go pretty fast through all of this because it's in these notes, it's in Prager and Hodge's book, and if you're really interested, I would recommend that you get a copy of the book because those guys have tighter proofs than I have recreated here. The situation is now that we've taken a material, we've said it's rigid, plastic, of course it's incompressible, and we've worked out the equilibrium equations, and we've come up with these two variables, omega and theta. Omega being related to the mean stress in this two-dimensional problem, and theta being the orientation of the maximum shear face relative to the x face. So these equations can be used to solve simple problems. The purpose of these solutions is to develop a feeling for all this. So that's what we're doing. You'll recall that when we write down the boundary conditions, we discovered that if we looked at a boundary where plastic flow was occurring, we could specify the surface normal stress and the surface shear stress, but we, in most problems, really can't specify the interior normal stress. And so there's a little bit of ambiguity there. On the beginning slide here, you can see how that manifests itself. The first three equations show the expression for M, that's the normal stress on the surface, sometimes called traction. T is the shear stress on the surface, and N prime is this interior normal. When we try to invert those equations, then we can boil down the two equations that are below the first three. And you can see that on the theta, there's a plus or minus. So this is the case where there are two more circles with the same normal and shear stress, and we've been through that before. So as we solve any problems here, when we come to a region that's got plastic flow at a surface where you're specifying the stress, then we've got to make a decision as to what that interior normal stress is. And this is something that would be easy for engineers. It might be a little more difficult for mathematicians, but the world doesn't end either way, because if you make the wrong guess, you'll figure it out. You won't be able to solve the rest of the problem the way you want to. Now, there are several schemes that are used to form the kind of solutions that we're going to get. And these come under the general category of slip line theory themes. And that makes a little bit of sense, because if you recall, on these first and second shear lines, those were lines on which the shear stress was equal to K. And so your stress strain curve will say that you're going to have shear on those lines. And we're going to take advantage of that in various places. Okay, first of all, there's the algorithms that are available to solve these kind of problems. I want to run through those very quickly. If you've had a differential equations course, you're probably familiar with this anyway. The The first problem is called the Cauchy problem, and I wouldn't begin to tell you what Cauchy did. It's just too embarrassing that someone that long ago was that smart. The way that works is this is the way the problem is being specified, is you're given a shear line, and I'm sorry, you're given a line on which the shear line properties are given. That is, omega and theta are known everywhere on this one line. Okay? Now, if you were trying to solve an elasticity problem, this would be very frustrating because you can't do it. But if it's this hyperbolic type equation, then things change. So on the next slide, there's a sketch where the heavy line is the line on which omega and theta are known. And the Hencky equations, the equations for the Hencky theorem, are given on the page. And as you can see, you can go along that line. You could start, if you really felt like it, on the points 1, 1, and 2, 2. Okay. Then, knowing theta, you know which way the shear line is directed as it goes through those points, the different angles, of course. And if I take a short enough little element, then I can draw a first and second shear line through each of those points. And that'll determine, if I started out the way I said, I would determine omega and theta at point 1, 2. And I could just keep going along that line and work out the points that are adjacent to the starting line. When I get those, now I have omega and theta at all those points. And I can then do it again with that second row of points. And I can keep going until I get to the point 1, 6. And then I'm stuck because Henky's theorem won't do any more for me. And what I have is a characteristic result for a hyperbolic equation. That is, given the information on the heavy solid line, I know everything within the domain of influence. And that's the little triangular looking figure there. Not that I couldn't have gone outside, but supposing that the heavy line is on a boundary, so I'm not really caring about anything with a slip line field outside. So this domain of influence is all that I can get, but I can get everything just starting with a line. And that's the Cauchy problem. The second problem is called the Riemann problem, another famous mathematician. And in that problem, we know what's going on a shear line, and then there's an intersecting shear line, and on that shear line, of course, we know theta. If we know something's a shear line, we automatically know theta. So there's a bunch of some simple equations that define what's going on. On the next slide, you can see the domain of influence. It looks more like a rectangle than a triangle. And on this, the way it's set up, it's the first shear line is CC, and that's the one on which things were specified. And the lowest intersecting line is the line on which theta is known. And it's a pretty simple numerical scheme. You can imagine taking small steps and generating that domain of influence. The The third algorithm, and this is the only one, this is the last of the three we'll talk about, is we specify on a line we specify that it is a line, and then on another line that's not a shear line, we specify omega and theta. And we come up here with another sort of triangular-looking shape for the domain of influence. So these are the schemes that you can use. They're straightforward. People actually did this years ago in the 50s, but I don't think there's any person alive still doing this. But it's in the textbooks because it's a way to understand physically. Well, that all has to do with the stresses. The case of the velocity fields is much simpler because what you know is that on the shear line, the shear stress is K. And what you will have is no extension on that line. It's just shearing. It might just be one layer sliding over another on those lines. So writing an inextensible equation along a shear line is pretty trivial business. There's a little sketch there showing a line that's a shear line, and below it are given the equations. V1 would be the velocity along the first shear line, and of course V2 is the velocity along the second shear line, and you get these simple little equations, and there's not much more you can say. But these lines have some properties, these shear lines. And one that we'll look at almost exclusively in these simple problems is if the shear line is straight. Okay? If it's straight, obviously, theta doesn't change. And that would mean that if it's a first shear line, that omega minus theta is a constant. So since theta is constant, omega is constant. So along a straight shear line, you have omega is constant. The other possibility mentioned here is when you have a streamline. That is, that the velocity perpendicular to the shear line you're looking at is 0. Then it is just a shear line, and it can have a curved sliding relative to faces. I mentioned that Prager and Hodge gives a rather obvious scheme for solving that. Now, a rigid plastic boundary in a material, that is, you come to the limit of the plastic region, and you're now going into the elastic region. It has to be a shear line or what's called a limiting line, which is something we'll mention in a minute. On a rigid plastic boundary, you know, the normal velocity has to be continuous. And in the rigid part, it's not moving. So the, if you like, boundary condition for the plastic region is also that the velocity, the normal velocity is 0. Now, on the next slide, we're going to look at a class of shear lines that's used in putting these things together. What you do is get a couple of little schemes together here, and you get like a French cook. You put a little of this and a little of that to form the solution to the problem you're trying to find. And if you're lucky, you can put something together, and we're going to show you some of those. The fact is that you can have what's called a family of straight shear lines. Family being used usually as there's the first shear line family and the second shear line family, and that's all the shear lines there are. Well, a simple case which really, I think, exhibits something physical about plasticity problems is that if I take a set of intersecting shear lines where both are straight, so remember now those shear lines are orthogonal, so you could draw a rectangular boundary around some of those. And if you went to say, what is the velocity field in here, you get this strange result given in the first equation, the first pair of equations on that slide. And you get that the x velocity is an arbitrary function of y, and the y velocity is an arbitrary function of x, which sounds pretty general, but it really isn't. Each one of those is the way that you could share a deck of cards, but you can also, not with a real deck of cards, but with a plastic solution, you can simultaneously shear in the perpendicular direction. So these are just a bunch of planes sliding over each other. You know on the shear lines that you've satisfied the condition that the shear stress is K. So these things can slide around and do a lot. This makes it pretty simple in many cases to find a solution because of the arbitrariness of the kind of velocity field that you can have. When only one family of the lines is straight, then that's called a fan. And in these notes, I've covered both of the kind of fans that Prager and Hodge cover in their book. But I think today I just want to talk about the one where it's called a centered fan. And that is all the straight shear lines intersect at one point, just like in the figure, at the point O. And the way Prager gives his illustrative problem is that the straight lines in that figure are first shear lines. Okay. So on each of those lines, theta is constant, omega minus theta is constant, so omega is constant. For the second shear lines, now to go from one to the other, the orthogonal set will obviously be circles. And as I go from one to the other, theta changes, and theta is theta plus omega is constant on the circular lines. So as I go along from straight line to straight line, the change in omega is equal minus the change in theta. And that's a centered fan. And the stresses are given here. That, you know, since r theta is a coordinate system that's lined up with the shear lines, then we can get that, as written here, sigma r equals sigma theta equals 2k omega, and that's equal to 2 times k times c minus theta, while the shear stress, the r theta shear stress, is always k. And for the velocities, you can get a general expression like the one given there. However, if, and that'll be this, what I'm about to say is going to be the case for the problems we'll look at. But if the point O is within the plastic region, then you can specify that as V sub O. And the solution simplifies a little bit, and it's given as the, well, it's given in the second to the last equation in terms of an h of theta. And if you look at the line above that, then you stick h of theta into those equations, and g of 0 has to be 0. And then you can come out finally with the last equation on the page, and it gives the velocity field that you can have. It's not unlike the shearing one, except now the circles are sliding on each other. Okay, going to the next slide. The case for the non-centered fan is worked out. I don't intend to go over that because we really don't need to do it to do the illustrative problems. And briefly, what it all amounts to is that there is a base circle, and that base circle, which is C dash line on the top figure, is generating the shear lines, and there's it's got a property that these lines are involutes of the base circle, but I don't think that it's all that important. The only good thing about that is that if you're old enough to have taken kinematics and mechanical engineering program, you might remember that gears are designed using involutes frequently. So it might remind you of the old days. There's a problem started at the bottom of this current page, and it's due to Prandtl. It's always the same guys getting in on the act. This problem is extremely simple, and it's one of those. It's not unlike elasticity, where you have to say, well, we don't worry about end effects. Everything not near the end is okay in the solution. Well, that's the way it is here. The end effects on this so-called slab problem, and also at the origin, the results are not to be taken seriously, but everywhere else you're okay. And what you've got here, remember, this is two-dimensional. So you've got a nice big thick plastic piece of plastic on a table, put a flat plate on top, and this is hard to do because one of the dimensions of this thing we put on the table needs to be infinite, but we can make it just long, and the other dimension much shorter. Then you put a plate on the top and push down, and so you squeeze stuff out, and you do things in a pretty straightforward way. And the solution is really quite simple. On the next slide, the solution is given, and you can see it's a quadratic in y and linear. It's quadratic in y and linear in x. And what you come up with there is it's shown in that picture in the middle of the page, where the shear lines have these very nice looking shapes, and in fact they're cycloids, and it's a set of orthogonal cycloids, and the equations give what the pressure is to do the pushing, and you can see that you have a solution there. It's really quite simple. On the other hand, physically, I've never really gotten too enhanced, too enthralled with that solution. But Prandtl did it, and everybody should know about it. The next thing to take a quick look at is what happens with lines of discontinuity. And in the case of velocities, if you have a velocity discontinuity, how would you ever get it? And it's really simple to imagine how that would happen. But the theory that we've constructed, let's take a beam, and of course now this has to be really a long plate because it's a two-dimensional problem. and we're going to bend it in the usual way you might bend a plate. So it's real long in this dimension, and I'm bending it like that. Well, first, remember that this stuff is rigid until it has plastic flow. So nothing happens at first because you need to get the region fully plastic, because you know how a beam bends. And then when that happens, you have the normal stress on the top equals, say, to tension, and the normal stress on the bottom equal to compression. And in the limiting case, and nothing happens on this problem until the limiting case, you get sliding at the neutral axis, halfway up, and one part will slide on the other. And that can be looked at if you know what really happens with a beam. That's kind of a limiting case of two plastic regions coming together. And that's almost always the kind of physical phenomenon that you have when you find such a velocity discontinuity. That being the case, you're going to have very high shearing on that line, infinite in fact, and then it won't be able to extend. And consequently, you can look at that in the case of this beam, is that layer that's halfway through it. You can look at that as Prager calls it an inextensible filament. And along that, you can bend it any way you want. It's got a general solution that just says that the displacement is just any old function of the coordinate along the filament. It's a little different when you talk about stresses, as you might expect. And at the bottom of the page there, there's a little picture showing the only kind of shear or stress discontinuity that we're going to consider. That is, looking at that picture, the line of discontinuity is LL in that figure. The normal stress across that line has to be continuous. Otherwise, you're going to violate the equilibrium equations. The shear stress, shown as T here, it also has to be continuous. And those two conditions are what we always use with boundary conditions to say that the stress on the inside of the body is the same as what we're pushing on the outside. The only thing that can be discontinuous is this interior normal stress. It's written as N1 and N2 with primes on it. And so now we're back in that same old situation where we have the two intersecting Mohr circles, and one side of the line is one of the circles and the other side of the line is the other circle. Going to the next slide. If we write the conditions for the continuity of N and T from those earlier equations that we had when we were just writing out what the normal and tangential stresses were, you get the first set of equations on this slide. And Prager was the fellow that figured out that the solution you care about is given by the second pair of equations on this page. And these things are called the Prager jump conditions. So we know omega and theta on one side, and These are the equations that have to be satisfied to solve for omega and theta on the other side. The interesting thing about that is that the discontinuity, when you work things out, the discontinuity splits the angle between the corresponding shear lines. And that's very handy because geometrically you can work problems without thinking. And that's the next thing that we're going to do now, is we're going to look at the first thing that I would call a real solution up to now. Okay, well, this solution is what I would call a simple solution for a wedge loaded by the pressure on one flank. And a cross-section is shown in the middle of the page there. And what's happening is that we're going to put a uniform pressure on the right side. We're going to leave the left side open, and we're going to push on it. And the only dimensional thing we need to worry about is this little angle beta. It's the half angle of the wedge. And if you go to the trouble to write down all these conditions we've been talking about, you can convince yourself that I can cook up a solution here where on each side of the wedge I have a region of constant state. That's the first thing we talked about with an orthogonal grid on each side. But because of the way things are, they've got to be, these stress fields have to be tilted. And when they're tilted, then where they go together, you've got to satisfy the jump condition. And one of the things that Prandtl discusses is what should I assume is the internal normal stress. Well, any engineer would look at that figure and say, I've got compression on the left and tension on the right, along the surfaces. And immediately that tells you which of the choices on the internal normal stress you should take. And this is just a matter of writing down what is obvious and combining it together. And on the next slide, the result turns out to be that the pressure is 2K times 1 minus cosine 2 beta. And in order to get there, you had to use the first jump condition above to get there. So you have a solution. It tells you what the pressure is. You can use those regions of constant state to figure out what the pressures are everywhere else. And if you set the velocity along the discontinuity to 0, then the x velocity along the discontinuity, which is vertical in that picture, is just any old function of y. Now, you can play around with discontinuities all that you like. There is one solution here that we're going to come back to later, and I'm just going to give you the answer on that. It was done by Windsor and Carrier. Windsor, as far as I know, was a student of Carrier's, and I can't tell you anything else about her. George Carrier, let's see, was born in 1918, died 2002. He got his master's and his PhD at Cornell. He ended up winning the National Medal of Science in 1990. Got the Timoshenko Medal, was a member of the National Academy of Sciences, and had a lot of things to his credit. The field he's best known for, I think, is fluid mechanics. But he came up with this, putting a bunch of constant state fields together and putting appropriate discontinuities between them. And the solution shown on this page is really 4 constant state regions joined, and he works out the stresses and the shear lines and all the rest for that. And in the long run, you can figure out what the pressure is at the top, and that's given on the next page, first equation. And it's a truncated wedge, and the solution is really quite simple. The pressure is 2k times 1 plus the sine of that beta angle, which is very much like the beta in that wedge that we just looked at. Okay, with all this as background now, I want to look at some of what I would call the classical solutions in slip line theory that you find in all the books. And as I say, nobody works problems this way anymore. They use them to get a feeling for plasticity. This, the first problem is a call to punch problem. It's not the kind of punch that you normally see. This is, because it's a two-dimensional problem, this is a punch that's real long in this direction, and now you're pushing it into a half plane of plastic material and trying to find out what the solution is. And what will happen, you can make some guesses, as you push on the plane, you will develop a flow field, and you've got to push the material that's under the punch to the side somehow. So you can see in that sketch that this was worked by putting 4 constant state fields in and joining them with some centered fans. And so let's see. On the boundary AD, of course, that's got no stress. And then the line AF is the boundary of that constant state region. That's a first shear line. And of course, then AG has to be a first shear line when you go through the centered fan. And what's happening when you go through that fan is omega's changing, and it's going to change by the amount pi over 2. And then you come back up to another constant state region. And knowing what omega is in that region, you can figure out what the normal stress is. So this it's a very classical problem, and now it says it's a lubricated flat punch. All that means is that the shear stress on the face AB is everywhere 0. So you have to be lubricated. This problem can be worked with friction, but that's not the case we've got here. We're taking the dead simplest case. And some of the gruesome details that it takes to get there are written down. The answer is a classic answer in plasticity theory, and that is that the normal stress that it takes for this punch to indent the surface is 2 plus pi, or about 5, times k. Well, let's remember now that 2k is the tensile yield point. K is the shear yield point. And so we've got a pressure that's about 5 times the shear yield point. And you would expect it to be pretty big because you're pushing into a semi-infinite solid. So the next slide shows some cute things about this solution. The first is the lack of uniqueness of the answers. So on this next slide, the first picture has, on each side, it's got half of a solution. So there's really two solutions being described here. The one on the left says that, well, the constant state region under AB is just one region of constant state. In the previous solution, it had been two. And some people argue, well, you see, on the first problem, you're pushing on that little point up at C, and it's supposed to be rigid, and for physical reasons people don't like it. But remember, all this stuff is for the incipient flow. So who cares what happens afterwards? That would be a more mathematical answer. In the case on the new slide, you've got a region of constant state that just goes straight down, and it maybe is a little more realistic. Then there's a sort of an intermediate solution where there's a little rectangular region in there that's a region of constant state. That's on the right side. But the remarkable thing is that all three of these solutions give the same answer. And when you get into some theorems that we're going to be talking about, that would be expected. So all of these solutions have velocity fields that can be associated with them, because, you know, although I can look at this and say what the stresses are, I still need to show that I can construct a velocity field that's consistent with those stresses in order to say that I have found a solution. And that's true of all three. Okay. Now, below the additional solutions is another picture where you can pretty easily see how they got the solution. And what they've done is taken a truncated wedge and just push it on the top. And you can see that the solution on that picture, you should be to the point now where you can just look at this thing and tell what all the shear lines are and more or less what's happening. In that solution, all they've done is take some angle off of the centered fans on each side. So they've brought it down a little bit. And because of that, the solution now depends on this angle gamma, which is shown in the figure. It's playing the role of beta in those earlier slides with the wedges. So that's fine until you fold up your centered fan. And what happens then is that you're just pushing on a bar in compression. And the solution is, you know, ceased to be interesting when you make gamma, would that be 0? Or as it approaches 0. Okay. Now, you can also have a different kind of a solution from the one we had before. And that's given on the last picture on that slide. And we're back down to the wedge with the uniform pressure on one side. And what it says is it's the obtuse wedge. And the reason it says that is that if you take your regions of constant state, the ADF and the ABG, if they are not spread with those angles of beta, so that 2 beta is more than pi over 2, then there's no space for the centered fan. But if beta is greater than 45, then you can put in a centered fan. Now, that's kind of funny because we had a solution before that looked pretty good. And it was for a wedge just loaded on one side, pretty much like this. And if you look at this answer, it doesn't quite agree with the earlier answer. And if we go to the next slide, there's a little sketch there. And this really, I think, is a place where you can catch some meaning on how plasticity works. What is there is a plot of this angle 2 beta in that last picture we looked at. And then we're looking at the pressure that it takes to induce flow divided by the U point and shear. Now, the two solutions, the one I just mentioned, and the earlier solution agree when 2 beta is less than 90. And they disagree when 2 beta is greater than 90. Okay, there's two things here. First off, why should they agree up to 90 degrees? And the reason for that is, if you go back and look, is that unless 2 beta is greater than 90 degrees, there's no place to put that centered fan. So about the only thing that can happen is the discontinuous solution. On the rest of it, we see that the answers don't agree. There's a solid line for the continuous stress field, and then there's a dashed line. It's a bit hard to see even in Brocker's book, but it corresponds to a load that's less than the load for the continuous field. So the second part of the understanding the mystery of this curve is that you might think, if I started out here, say at 2 beta is 150 degrees, and I went straight up to find what the load for plastic flow is, I would first come to the discontinuous stress field, and then I would come to the continuous stress field. So a neophyte plastician might say, well, the one that can happen first is going to happen. But that's not true. The continuous stress field is the correct answer. So then, why is the discontinuous stress field not the right answer? And it's not the right answer because on the what did they call this? The obtuse wedge. When you have the discontinuous field, you can't find a velocity field that goes with the stress field. So if you can't find a velocity field that goes with the stress field, then you don't have a solution. And that's the case here, where this discontinuous stress field is below the solid line. So in fact, you would have to go to the higher point when you're past 90 degrees in order to find the correct flow solution. Okay, now there's a couple of classes of solutions that people solve, and they're a little bit different, but it's the same old stuff that you use to solve the problem. But at the bottom of the page there is shown an extrusion problem. So you're extruding a sheet through these two lips here that reduce the thickness. Now people have worked the three-dimensional problem, but like drawing a wire. But that's a lot more complicated, and we're not looking for complicated problems here. We're trying to get simple things that we can understand. Well, this one is simple because he's first of all, it's limited to a 50% reduction, which then means you can put in these centered fans as indicated, and you have then a uniform stress field for the stuff that you're pulling out. You're just pulling in tension. On the left, there's no pulling going on. And of course, we're going to assume that the die is frictionless. That just always makes life simpler. And you can then work out, using this stress field, what load it would take to pull the sheet through the lips and thereby make the sheet 50% thinner. That problem gets worked in some detail in Prager and Hodge. And although the notion of finding velocities there are simpler equations tracking exactly what the path of a particle is in this problem it's mathematically inconvenient, I guess I'd say, but it's done in the book. The difference here and the other problems is that we had a statics problem before, and we were just looking for the load to start flow. Here, this is really a continuous flowing problem, and in that sense, it's physically different, but you can use the same sort of equations. And as long as you can find the stress and velocity fields, you've got a good solution. There's another class. Oh, I should mention that the amount that you have to pull is given on the next page, and the stress for, I guess this is, we're extruding, so we're pushing on the left, and on the right we're not pulling. I said that backwards. Okay, so we're pushing on the left, and the pressure we have to push with is 1 plus pi over 2 times k. The next kind of problem is referred to by Prager and Hodge as pseudo-steady. And this is a problem that the geometry is actually changing, but it's remaining similar. All it does is enlarge. So since the configuration stays the same, you have the opportunity to use these equations that we have to work out what the solution is. So if you look at the figure, the only figure on that page, what we've done is we've got something that looks like a knife, and it's being pushed into a loaf of bread or something, and at least plastic bread. And maybe silly putty would be a better thing to be cutting into. Anyway, as it goes down, once more, the material's got to get out of the way because the material's incompressible. So a little ledge rises on each side of the punch as it goes straight down. And you can see it's the same old thing. On each side, there's two constant state regions, and in between, there's a centered fan. Now, the geometry of this is sort of hard to scramble through, but all that Prager and Hodge give is a curve that gives you the relationship between gamma and beta. And once you know gamma and beta, you can find everything you need to know. Gamma is the angle on the centered fan, and beta is the wedge angle, the half wedge angle, as always. So I scrambled through the algebra, and I worked it out and generated my own curve, and sure enough, it agrees with Prager and Hodge. But checking Prager and Hodge is a futile thing usually, because they never make a mistake. So that's those are the principal kinds of problems, and those are the only ones to really, I think, the only ones you need to see to get that feeling that you need, the feeling that Dan Hartog talked about, feeling it in bones. So now we turn to yet another part of plasticity, and it's a relatively mathematical part. The objective is, since these problems are so hard to solve, or they were in 1950, now you toss them into a computer program like Abacus and never think about it. But since these problems used to be hard to solve, they've developed equations and techniques to use that establish upper and lower bounds. This happens in a lot of areas in mathematics. Essentially, if you look in elasticity at all those energy methods, they are establishing bounds. And what's going on here in this next part is the same sort of thing. This is getting upper and lower bounds on loads that it takes to initiate plastic flow. On this slide that follows the one about the pointed punch, I've got a little review there. I don't know why I put this in exactly, but it seemed to me it might be good to remind people of a couple of things at this point. The first equation on there gets called several different names, Gauss's theorem, this and that and the other, but it's just converting a volume integral to a surface integral. So that's there if anybody wants to, as we go along in some of this messy stuff. You can always go back here and confirm that everything's legit. The thing that's sometimes called the equation of virtual work, called principle of virtual work, various things, is written out here in tensor notation. So it works in several forms, but what you're doing is you're saying, and let me say this: if I was going to do this again, I would put a dot over the strain and the displacements to convert them to strain rate and velocity, because that's the way we use it most of the time, because that's the way in plasticity you normally think of things, as stresses and velocities. And so if I would put dots as I indicated, the left-hand side of that equation is really, it's the work being done by the stress field on the strain rate field over the body. And we're going to use that first equation, and then we're going to fiddle around some more, and we need to use the equilibrium equation. But that's really the only equation that we need to keep struggling along. And well, you could say we're using another equation when we convert the stresses on the boundary to the so-called boundary tractions. And we've, that's the N and T business that we've been through about 3 times by now. So this says the work being done on the body is equal, the work being done in deforming is equal to the work done by the external loads. If you paid a lot of attention in thermodynamics, that begins to sound a lot like the first law. And the difference is that in the first law, you would have to say what happens on the left-hand side. In the case of plasticity, if you had plastic plasticity, you'd say, well, some of that gets stored as strain energy, that's the elastic part, and some of it gets dissipated probably as heat, or the temperature of the body goes up. And if you do a stress strain test with the usual sample, if you pull it pretty fast and reach over and touch it after it's necked and so on, it's warmer. There is energy lost there. So you're not really too far from the first law on this. The next couple of equations is reminding you the relationship between the surface tractions and the stresses at the surface. Some odds and ends on polar coordinates, and the Schwarz inequality. It's got a name that's much too fancy for what it really says, because if I take a couple of two-dimensional vectors, and I said A and B here, so I have AX times I plus AY times J in the usual complex notation. All that the Schwarz equality is saying is that if I take the length of the first vector and I multiply it by the length of the second vector, that's going to be greater than excuse me, the square of the dot product of the vectors. And you know the dot product can be written as the length of one times the length of the other times the cosine of the angle between. Cosine's never greater than 1. Schwarz equality has to be right. But Prager and Hodge use this in a couple of proofs. So it's good to have a little piece of paper here to remind you, I think, of what's going on. Okay, well, now we're going to go into some of these schemes for getting upper and lower bounds. And the theorems don't have to be as limited, even as Prager and Hodge make them. And it's the same old thing. You can extend stuff, but that makes it more complicated. And the first time through, it makes it harder to digest. So to start out, there's a review in Prager and Hodge about the principle of virtual work. We know all about that. We're going to, at the beginning, start, as he does, with continuously differentiable, with respect to x and y, stresses and velocities. No body forces. We're going to only look at the principle of virtual work in cases where the stresses satisfy the equilibrium conditions. And the velocity field is such that you can derive the strain rates from it, and we assume then that definition holds. And then the boundary load, boundary traction equaling the inside stresses holds. And then you get this last equation on the page, and I discussed that. I just discussed that on that equation, on that page with a bunch of equations on it. There's a proof here, which I don't want to fool with because I think we already know that. And what is used in the derivation concerning these upper and lower bounds is what you could call the rate version of the principle of virtual work. And that's just that you look at the strain rates, you also look at the stress rates, and that's needed for part of the derivations for the theorems. Now, there's a little bit of discussion here about the contribution to the principle of virtual work caused by discontinuities. And that comes out to be pretty straightforward. First off, you don't need to do anything for the stress discontinuities that we're allowing, and that is the stress discontinuity for the interior stress. On the velocity discontinuities, you could guess how it would contribute, because the principle of virtual work is really an energy type statement. So if there's energy dissipated somehow or another at a velocity discontinuity, you've got to throw that in the hopper because you've got to account for all the energy going in all the different places. So what it comes down to is that if you have a velocity discontinuity, then the shear traction across that times the velocity discontinuity times the length of the discontinuity, or the integral if the shear stress varies, has to be thrown in. And we'll see how that's done. I mean, this is very straightforward. So that if we go to the next slide, the principle of virtual work, both in its original form with the stresses and strain rates, as well as with the stress rates and the strain rates, are shown at the top of the page. Now, we'll do a little bit. I'm going to discuss these theorems. I've got the proofs here. I find them a bit awkward to comprehend. So I want to just talk about the theorems, and then we're going to do some things. But later, I've got another derivation that was done by someone else, and not in competition. He was a friend of theirs, Paul Simons, and I really prefer his derivation to the one that's in Prager and Hodge because it's so much simpler. And what we're doing is called limit analysis, and there are the theorems of Greenberg, Drucker, and Prager. Greenberg went to work for the government and became some kind of a manager or something, so he never got heard from much again. I've mentioned Prager. Drucker is hard to explain. When you try to Google Drucker, you can't find him. I suspect maybe some of his relatives have taken everything off. Drucker was one of the most influential mechanical engineers that I've ever known. Little things like he was president of American Society of Mechanical Engineers. He was president of the American Society of Civil Engineers. He was president of the American Society of Engineering Education. And in spite of that, his contributions to plasticity are amazing. There's a thing called Drucker's postulate, which we will discuss later, which has to do with the underlying stability of a material. He is, of course, a member of all these societies. He won the Timoshenko Medal, and you can just go on and on. But apparently is practically being kept as a secret to from the general public. Anyway, Greenberg, Drucker, and Prager get the credit for laying out this stuff called limit analysis. And all it is really is bounding theorems. So I want to just go through what these bounding theorems are, and that's what is starting on this page following the principle of virtual work equations. So first off, they only look at two kinds of boundary conditions, and they only look at the two-dimensional problem. So we're really using the same equations we were just using for slip-line theory, and we're just doing something else with them. So the first boundary condition is that on part of the boundary you specify these surface tractions, T and N. And the second kind of boundary condition is that on that part of the boundary, the velocities vanish. They don't have a finite value, they vanish. So the entire boundary is made up of just those two kinds. So we're looking at a certain restriction on the kind of problems that we're going to look at. If you want to have the ability to determine the displacements, this is, I think, obvious, you've got to have part of the boundary has to be the boundary condition number one, the stress boundary condition. You've got to get things loaded somehow, because you can't move the other part of the boundary because the velocity is zero. So that's pretty obvious why they have to do that. The notion of proportional loading is part of this theory. And what is meant by proportional loading is, imagine you have a body and you have a bunch of loads applied to it, maybe 10 different loads. They all have to grow in proportion, in the same proportion. So you can write them as a function of, say, time times some number, and then you gradually increase monotonically the function of time. The loads go up, and eventually you're going to get unrestricted plastic flow. That's what the whole thing is about. So they call this impending plastic flow. And also the linearized strains and displacements are used throughout this derivation. But that's not really a restriction for the kind of problems that you're working. Okay, now they have an awkward way, in my way of thinking, for defining things. But you have some reference loads, and you can just, if you have a pressure on something, and that's the only load, make it 1 psi. What have you got to lose? Put it in there, and that'll be your reference load. Then there is a load at what Prager and Hodge call impending plastic flow. So that's when things start to go. And being rigid plastic, nothing happens as far as displacements go until that happens. Okay, then so this factor of safety S is the ratio of these actual collapsed loads, if you want to call them that, or impending plastic flow loads, to whatever this reference load you've got is. So in actuality, if you just take a tiny load, your safety factor could be 100, could be 1,000,000. And they say, well, it has to be greater than 1. Well, that's more a mathematical concern than a practical one. Anyway, so we've got this safety factor, and where we don't have it, we're trying to find the safety factor. That's what we're up to. And we're going to have a way to establish first a lower bound on S, and secondly an upper bound on S. And the way we find the lower bound is we have to find a statically, what they call an statically admissible stress field. In a way, it's kind of a guess, because this isn't a full solution, but it's part of a solution. And once more, if you think of elasticity, you do things, minimum potential energy type theorems. You guess some displacements, you toss them into the potential energy, you minimize it, you get a load, and you say, well, for these displacements, this is as good as I can do. Well, okay, here we're going to guess some stresses in this first theorem, and the second theorem is more like the principle of minimum potential energy. So we have to find these stresses. So what do? They have to satisfy the equilibrium equations. And that makes them eligible to be stuck into the principle of virtual work, because in the derivation for the principle of virtual work, you had to use the force equilibrium equations. We have to be able to satisfy boundary conditions of the first kind. And then everywhere in the stress field, we have to satisfy the Mises inequality to say it doesn't yield. So what we've done is we've found a stress field that's okay as far as these equilibrium equations go. It's okay as far as the stress boundary conditions go. And the stresses in this field don't exceed the yield point. Well, if you find such a stress field, then you can multiply whatever stresses you've just figured out by some number, and what you would do, I mean what any reasonable person would do, is they would edge that multiplier up until they got yielding at least one point. And if that happens, then you say, well, I can't still have a statically admissible field if this multiplier goes up. And so that's what they call M sub s, is the highest multiplier for the reference stresses. And the first so-called limit analysis theorem is that MS has to exceed S, which is a complicated way of saying that the load you calculate this way is less than the actual load that it takes to collapse. And that's what I said was kind of awkward, doing it with this safety factor and multipliers and such. But it's perfectly good sense that something like that would be true. The second kind of bound that you can set is using a kinematically admissible velocity field. So what does that have to do? It's got to be incompressible. It's got to satisfy those boundary conditions where the velocity is 0. And there's a third step here given at the bottom of the page, which is simply saying that the boundary loads that you have to do positive work on the velocity field that you guessed. If it doesn't, change the sign. And if it doesn't do any work, if it's 0, then you're really missing the whole point of the problem. So you ought to go and reconsider what you've done. Okay. Now, if you get that far and you have your velocity field, then you calculate on the next slide. You calculate this thing that looks pretty complicated that really isn't. It's this M sub k, and what it is, if you look carefully at that, is it would be the work done if everything was yielding all over the place, divided by, well, I call it the internal work, divided by the external work. And this gamma dot, capital gamma dot, you can see is really, it's just the maximum shear rate that you have. So you look at that, and it's not nonsense. I mean, you may not be able to just look at it and guess its a bounding value, but there's a certain physical sense to that. And this second limit analysis theorem says that once you calculate mk, it's an upper bound on S. S can't, excuse me, S can't be greater than mk. So in the long run, you end up with this expression that ms is less than or equal to S is less than or equal to m sub k. And that is the primary result from limit analysis. There's a simple little problem here that is really discussed in Prager and Hodge more than it's worked. But I think you can see how it would all work out. This is a case of a bar that we're going to, let's pull it in tension. And the bar has two semicircular grooves in it. And the width of the bar is 4a, and the radii on these notches is a. Okay, so it's a reduction of half of the cross section at the smallest cross section. And the picture on the left here is the picture from Windsor and Carrier that we have a solution for. And if you happen to have a slip line solution, then you can put it in there and it will satisfy everything you need to satisfy to be a statically admissible solution. And you see, you've got to fiddle around here because that little truncated wedge should come in tangent to the circular notch. And so there's obviously a little bit of fiddling with the geometry, some calculations you have to make. But taking the result of Windsor and Carrier, which was that the load was 2k times 1 plus sine beta, you can scramble around and figure out then that your multiplier, and we're just calling T the load. So the multiplier is 1.26 k over t. So that sounds pretty good. On the velocity picture, it's usually easy to select these velocities. And in fact, if you think back of using the minimum potential energy theorem in elasticity, you can always dream up some kind of displacements that to you make sense. Well, this one is really dead simple. What you do is you take a line 45 degrees, because if I have uniform tension above and below, then the angle for my shear line is going to be 45 degrees to that axis. I'm going to take that top part that's crosshatched and say the velocity is going to move up parallel to the shear line AB. So it's just simply shearing on one plane, and everything below stays fixed. That's pretty simple. When you work out what's going on, the only thing you have there is looking at the equations above those pictures at the top. If you look at what it would take to calculate that, for the upstairs part of that m sub k, you have just simply the velocity discontinuity coming in. And the capital gamma dot is 0 everywhere, because you don't really have any strains anywhere except very locally at the shear plane. It's where the sliding's going on. Downstairs, you're just doing the work done, calculating the work done by the load as the thing slides up on an angle. And you come up then with 1.5 k over t as your kinematic multiplier. And you can see then that the theorems say that S, the actual solution for this problem, is somewhere between 1.26 k over t and 1.5 k over t. That's not bad, 1.26 to 1.5. It's not bad particularly when you consider in plasticity we got a lot of variables out there that we don't always know very well. We've got work hardening, we've got all kinds of things going on. So I think it is nothing wrong with saying that's a good answer. So I follow this by a proof of the two theorems. And I really don't think we should go through that here. it's there if you want it. The proof that I like is the one by Paul Simons, and we'll get to that. So I'm going to skip, let's see, that page that has the answer. I don't want to say any more about that. And the next page, still, these theorems go on. And there's this really slick stuff in there if you like theorems. But most people don't, I know that. Okay. When you get to the next figure in the notes, then that is another one of these cute solutions. And there's a certain part about finding these solutions where it helps if you can do something cute. Well, here, the problem we're looking at is, remember, two-dimensional problem. So we've got a very long hole in a square bar, and the hole is centered in the bar. And I want to know at what pressure this thing is going to start to flow. And we've worked problems where we know the answer, really, to this. For we know enough to just write down what's going on. Because if you see the dotted or dashed circle that's touching the square rod, I guess, then if you think about finding a statically admissible solution, you can ask yourself, well, what's wrong with grabbing that solution that I got back when we were working the cylinder problem? The answer is nothing wrong with that. So you can just go back and grab that cylinder problem, and the statically admissible multiplier will be just whatever that load is. Furthermore, we showed that there was a velocity field that went with the solution for the cylinder. And we can take those little distorted kind of triangles at each of the four edges. And we can put the velocity field that we found from the earlier solution for the cylinder in there. And, you know, there's so much flexibility on these velocity fields that you can then show that they are compatible with the, a region like, let's see if we can figure this out, A, B, C, D, E, A. It's a chunk up at the corner. We can just have that move as a rigid body and go scooting out at 45 degrees. And so I've also found a kinematically admissible solution for this problem. And it's the same solution I used for the statically admissible. It's got the same pressure, obviously, because it's the same problem. And so I know that the actual pressure that it takes to initiate this impending plastic flow is just this P double star, which was 2K times the log of the outer radius to the inner radius, which would be the ratio from the dotted circle radius to the inner circle radius. So that is cute. We've got an exact solution for a problem that in elasticity would be quite awkward to solve. But in terms of limit analysis, it's practically trivial if you know the cylindrical solution to begin with. So there's little tricks that can be played here and there. In the next page, there's a problem with the tension on the semicircular pieces. And instead of the kind of bizarre velocity field that we guessed before, we can also grab that cylindrical solution and do the same thing on those little triangles that we did on the previous page on those funny looking triangles. And so I can come up with at least an upper bound solution for that problem. So those are simple little problems, good to understand and appreciate. Another kind of problem that you see in limit analysis, and it's received a great deal of attention more by civil engineers than mechanical engineers, because mechanical engineers are, on average, more likely to be dealing with machine parts or something like that, and civil engineers are trying to build a building, and so they've got frames and beams and that sort of thing. But here's a picture of a beam. It's statically indeterminate, as we used to say in strength of materials, and it's a cantilever beam on the usual pin connection at the extreme away from the built-in end, and some distance back from the end is a load P. So the length of this thing is L, and the location of the load is given by P. And I have some reaction over here, R. Okay. Now this problem, if you just stop and think and look at it, you know, what's going to happen? Well, one thing you need to remember is that if you look at the absolute value of the moment along a beam that's loaded at the ends and no loading in the middle, the maximum value of the absolute value of the moment has to be at the ends. It doesn't happen in the middle. And think of the shear diagram, and you can convince yourself pretty readily that that's the case. So I've got, in effect, two spans here. One of them's length is A and one is L minus A, and wherever there's going to be some moment that's going to cause failure, it's got to occur at the built-in end, at the load, or at the end. But there's other things about this problem that restrain you, because you can't just have the moment come up to the so-called limit moment. That's the moment where it's just going to bend without any increase in moment. I've got to have a displacement field to go with that. So I could work out some theorems for this sort of thing, but the thing to do is to say, well, what could happen? And if you think of the kinematic problem first, if I'm pushing on this thing and the load and the displacement under P starts to grow, then I've reached the impending load. But and I'll have a change in angle under that load for the two pieces. But I'm going to have the limiting moment at each end as well. Or sorry, at the right end. I have to have the limiting moment as well. Well, if under the load P there's a lateral displacement, I have to have that limiting moment at the connection where the built-in beam leaves the wall, and I have to have a rotation at the far end. And really, there's no way out of this. There's only one possible configuration. So you can figure that out. And I do below, just write some equilibrium equations. And at each of the places where there's where the moment equals this thing I call M0, that's that limiting moment, that occurs at A and at L. You take those conditions that has to be simultaneously satisfied in this problem. You put that into the equilibrium condition, and you come up with the load is this m0 over a times 1 plus a over 1 minus a. All right. That didn't require any limit analysis, but the reason I put this in is it shows something. It shows that when you have things like frames, then you have certain restrictions. And in this case, there's only one mode, so there's very little else to do. But in frames, that's not always that simple. Okay. This beam, this statically undefined beam, only had the one mode of failure. But if you look on the next, and not the top picture, that's just elaborating more on that particular problem we just looked at. But below that, there's some pictures, and they come from Prager and Hodge's book. But now, if you take this one where you have the load P at the 1/3 point and the load 2P at the 2/3 point on a built-in beam, you can't get away with what we just got away with, because it could fail this way or it could fail that way. You'd guess that you'd have to have your limit moment occur under the load 2P. But what about at P? Does it just stay straight as it goes through P and then bends at the ends? Or how does it go? Well, you can use these limit theorems and investigate those cases. And in the problems that are shown there, you could work these out, and what it comes to, if you fiddle around a little bit, there's a finite number of possible shapes that you could fail in. And if you evaluate, say, using the kinematically admissible fields, if you evaluate all of the possibilities, then you know that every one of those numbers that you've calculated has to exceed the collapse load for that structure. You just take the lowest one, and that has to be the answer, so you don't have to go any farther. And it's in that sense that the work done by civil engineers differs a little bit from the work that is being described in Prager and Hodge. Because in Prager and Hodge, you just have a field of displacements that's infinite. And so you've got to be smart enough to guess something reasonable, and maybe you get a good answer. In the case of these structures with a finite number of failure modes, then you can actually just pound out the result. And the techniques that are used are really quite different. So that's about all I want to say about the Prager and Hodge limit analysis of the part that's in, well, mainly in Chapter 7. So we move on now to something that Prager and Hodge treat as different, but it's not physically really that different. It's taking this two-dimensional stuff worked out by Prager and Greenberg and Drucker and writing down the equivalent mathematical results in 3 dimensions. And that's Chapter 8 in Prager and Hodge, and he calls it extremum principles. Well, of course, that's what we were just doing, is extremum principles on a certain kind of problem. Now, the proof on this is done in tensor analysis. And if you know tensor analysis, it's actually easier to follow than the two-dimensional derivation. And if you don't, it's probably a lot harder. So I've decided I'll skip that and So I am ending up going to a page where those derivations end. And I'm going to pick up where it says three-dimensional applications of limit analysis. If you start looking through the literature, places like Journal of Applied Mechanics, that's part of the ASME transactions, you find, well, not now, but back in the 50s, 60s, you find a lot of these kind of limit analysis problems being solved. And you'll find virtually no three-dimensional applications of limit analysis. I, at one point in my life, was very interested in things called Bingham fluids. Now, a Bingham fluid, the easy way to explain it is, it's got a yield point, but once you exceed the yield point, it's just like, exactly like a linear viscous fluid. So there's none of this stuff about that lambda parameter and all that. There's no such thing. Once you pass the yield point, you just have the regular flow. Well, if you look carefully at the formulation for a Bingham fluid, you find that the limit theorems apply for Bingham materials as well as for plastic materials. For a while, I was misguided. I misguided myself and convinced myself that velocity discontinuities could not be included in the Bingham fluid properties for the limit theorems like they could for the plastic. And this fellow Don Wood, he was a grad student at Rice, was interested in working a problem, and we tried to work a three-dimensional problem. So the first thing I said was, well, we can't have velocity discontinuities. Poor Don Wood struggled with that and called me one day and said, I think you can. And over the phone, he had such a neat proof that I realized the error of my ways. And that's the good thing about having graduate students around, is that sometimes they shake you out of your bad conclusions. So once Don had shown that, then the problem he tried to look at was really related to a drilling problem where you have cuttings in the annulus of a well, and maybe you've had to stop pumping the mud. So the particle then starts to settle. And one of the characteristics that you put in these fluids is that you don't want particles settling back on top of the bit, and then you can't get the bit started, and it's just one problem after another. So they make these muds so they have a yield point, and they actually measure it, and these are well-established properties. So the question would be, for a given density and say maybe diameter of a he took a sphere because that's the easiest. Take a sphere, put it in this Bingham material. How much yield point do you need in order to keep the sphere from settling? That is, how strong does the Bingham yield point have to be to keep the sphere stationary? And poor guy really suffered. He had one heck of a time. I think he tried everything. And I've given the result here at the bottom of this page. There's this, you're looking for this critical parameter, C. If you know what C is, then you can either find K, or you can find the difference in density between the sphere and the mud that you would have to have. And it turns out the radius of the particle comes into this. So in spite of Wood's diligent efforts, he put the bounds on it, on this value of c, between 5.75 and 12.25. Now this is a very big spread, and when you look at those two-dimensional plasticity problems, no one would ever be satisfied with a number like this. But I really became convinced, that this is the way it is in these three-dimensional things. After he did this, he submitted this paper for publication, and it got turned down because the limits weren't close enough. And I think that was not perhaps the best thing that journal could have done, because really, it turns out that in three-dimensional problems, it's just very hard to nail things down. Now, years later, see, Don's thesis is 1965, and in the next page, there's a reference to a paper in 1985, where some fellows did this on a computer, and they found that C is 10.49. So he was closer to the kinematic limit than the static. And I think that's also reasonable, because when you're guessing a stress field, particularly in three dimensions, you've got to satisfy all the equilibrium equations, and that gets to be a little more difficult than doing it in two dimensions. So anyhow, my conclusion out of all this is that you're probably not likely going to find many three-dimensional solutions that nail things down much closer than the order of 2 to 1. That's just my own conclusion. That's really the only case I can cite for a three-dimensional. Moving on, I've got a problem here that I'm working, and you can tell I'm just doing a lot of stuff that I think is useful to know if you're going to practice anything in plasticity, because all of these things can jog your memory and help you figure out what you're supposed to be doing. So this is a almost trivial problem. What we've got here is on this slide that says an elementary structures problem is three bars, really. There's no bending or any of that kind of stuff. These bars are interconnected with pins, so there's no moments. And there's symmetry about the vertical axis. So I'm just going to pull on this thing, and I want to figure out what's going on. Now these bars are elastic, perfectly plastic. So they go up, they yield, and the load stays constant, unless I reverse the load. And with a bar like that, if I pull, starting with 0 stress, I go up to the yield point, and then if I decide to compress it and yield it the other way, I've got to go twice as far. I've got to remove the stress I've already put on, and then I've got to go re-yield it. So you take this problem, and it's all written out here, but I think it's incredibly boring to go through why delta of the second bar is delta of the first bar over the square root of 2 and all that kind of stuff. So it's here. If you want to struggle through it, that's fine. There is a point to my having worked this problem, however. And that appears on the next slide, where there's a graph of, well, it's a dimensionless load versus a dimensionless displacement. And it's like a stress-strain curve. This curve is drawn to scale, at least as I remember when I drew it to scale. And the remarkable thing, I guess, I would say remarkable, is that if you look at that curve, what's happened is we've taken that load P And we started at point 1, and we got to point 2 where one of the bars, the central bar, yielded. So the resistance to increasing load drops off. Then we get up to point 3, and both bars have yielded. So I can keep on pulling because I'm using small displacement theory and all that. And I get out here to 4, and I decide now I'm going to take the load off, and not only that, I'm going to put it in compression. So when I start back from 4, the bars all unload. So the slope between 4 and 5 is the same as the slope between 1 and 2. And similar arguments will lead you to believe that the slope between 5 and 6 is the same as the slope between 2 and 3. And obviously the slope from 3 to 4 is equal to the slope past 6. What's interesting is that I can construct the curve from 4 on by doing the following fooling around. I can take the curve from 1 to 4 and take it off to the side. I can magnify it by 2. I can flip it about the x-axis to a 180-degree turn and flip it about the y-axis, and then come back and take the point that's the new 1, go put it on point 4, and it will line up exactly with the curve I already have. And the factor of 2 is sort of believable because, as I just said, when you pull a bar and then you push it, you got to go back twice as far. So that part makes sense. Well, a fellow, I've seen his name written a couple of ways. It's a real old paper, so I think it's suffered from age. But it's called Massing's hypothesis. And if you go start looking at stress-strain curves, they're a little like that. And people have sometimes made a lot over that. When you think about it and look at it, you can ask yourself the question, well, suppose I take the usual steel tension bar, polycrystalline material and all that, and you pull on it and push on it. You get this so-called Bauschinger effect. And how does that Bauschinger effect compare to Massing's hypothesis? And Massing's hypothesis exaggerates, well, it comes down farther than the actual load would come. And nevertheless, it's higher than you would get if you just say, I yield the same when I come back. So it usually turns out when people have tried to make some sense of Bauschinger's effect that you get something between no work hardening and Massing's hypothesis. When you start to test single crystals, you get closer to Massing's hypothesis. And I think that's because what happens in a single crystal is more like what these bars are doing, and they don't have the built-in work hardening that you would get from dislocations and such in a polycrystalline material. So I just wanted to point that out because it is going to come up later as we talk about something else. But right now, I want to go to the next slide and have a look at Paul Simon's derivation that I promised. He knew everybody too, and just about everybody wrote something that if you were anyone, you wrote something. And Paul Simons was certainly someone. Paul Simons went to Cornell, got his education there, went to Brown, and taught there for the rest of his life. He was a very gentle, gentlemanly unaggressive kind of person who was very smart. And my wife and I got to know Paul and Elise Simons, and I liked them very much. I liked them so much that I even liked their dog. And this is very unusual for me, because I don't like dogs in general. But even the dog, it seemed to rub off on the dog, and it was a very, very nice dog. So Simons wrote the section in this Handbook of Engineering Mechanics about limit analysis. And all I want to do here is go through his proof of the theorems. And I still don't want to dwell on them, but he goes right to the point. And Prager and Hodge are much more mathematical in their descriptions and covering all the possibilities and all that. In math, you really need to do that, but in engineering, you frequently really just need to know the essence of what's going on. And I think Paul did a good job on this. And he's got it in the form of 3 theorems. Well, that's the way that Prager and Hodge have it, because the first theorem is essential, and that's to say that when you reach this impending plastic state, that the stress rates don't change, because you need that to prove the other theorems. So he's got a proof here, and all this stuff is based on the principle of virtual work. So theorem number 1 is just showing that the what I've written here is sigma ij dot is equal to 0 throughout the body. And I think it follows directly using plasticity theory, and he simply writes the principle of virtual work, says that F dot, those are the boundary loads, and T dot equals 0. I'm sorry, the F dot is the body force, and Prager and Hodge throw that out before they even start. But he puts it to 0, then he puts his tractions to 0. He ends up with a modified form of the principle of virtual work. Okay, so he comes down then to the second equation. And if you remember, if you have the combination of having the Levy-Mises stress-strain equations, the Mises condition, and no work hardening, you take those 3 things and put them together, then this term sigma ij dot times epsilon plastic ij dot, well, ij, sorry, equals 0. So he boils down that second equation into this, and if you look at that, he's got the stress rate times the strain rate elastic, and that's integrated over the volume, and that's equal to 0. Well, an elasticity theorem, that's the work, that's the strain energy, and that quantity is positive definite. And so in order to satisfy the principle of virtual work, you have to say that sigma ij dot is 0. To me, that's a nice, simple little proof. You can, it's easy to follow, believable. Then on the second theorem, writes the principle of virtual work again, and he does just exactly what Prager and Hodge do, really. But when he boils down his principle of virtual work, he ends up with the, well, it looks like the last real live equation on that page, the integral of sigma ijc minus alpha times sigma ij prime. Okay. Now, sigma ijc is the actual solution. You don't know it, but you don't need to know it. It's the actual solution. And what he's trying to do is compare a statically admissible solution with the actual solution. And this, he does the same thing pretty much as they did with safety factors. in his derivation. It's just like Prager and Hodge. Anyway, he ends up saying that the actual stress minus this alpha is that multiplier. It's like the multiplier that Prager and Hodge use. And it multiplies his guessed stress, which is a statically admissible stress. And it says this integral with the plastic strain rate has got to be 0. If you remember how the yield surface looks, the fact that the yield surface in the pi plane is circular, that the the plastic strain increment points radially outward, then you have to conclude, you see, that this guessed stress field can't be satisfying the yield condition. It can satisfy the yield condition, but it can't exceed it. And through straightforward arguments, he says this quantity has to be greater than 0. And if alpha is less than 1, then that's not going to be true, and you would violate the virtual work, what he calls the virtual work theorem. And so that proves that the load that you've guessed is a lower bound on the actual. Have a look at Paul Simon's derivation that I promised. And I found this in this Handbook of Engineering Mechanics. And I feel compelled to say a few things about these fellows, because I knew enough of them to want to say something about them. The fellow that edited this handbook was Wilhelm Flügge, and he ended up in Stanford, and I had the pleasure of meeting him on one occasion. And his wife kept a double name, and so in the work she did, it's listed as Flügge Lotz, L-O-T-Z. He wrote a very good book on plates and shells, and it was derived in a way that things were done back in those days. A lot of pictures and sketches and so on, and it was really a good text. But the derivation obviously had some problems. There were certain kinds of problems you could work that you knew you weren't getting the right answer. And eventually, a fellow named Erich Reisner at MIT sat down and with an energy method, this is all elastic plates and shells, he improved the derivation, and then Flügge's book became a little less popular, but it's still got a lot of good stuff in it. But anyway, there's a little interesting story on the side here of both Flügge and Flügge Lotz were at Göttingen. That's Prandtl's place. You couldn't be in a better place. And he was a privat docent, which is sort of a postdoc situation in Prandtl's place. And Flügge Lotz was a junior engineer working in the group. And so she didn't quite have the status that he had. And the story goes that when they served tea in the afternoon, as they always did in those days, and they still do in a lot of the British schools, and I think it's a good thing because people get together, they chat, and it's usually a very proper sort of setting. Anyway, the people that were serving the tea wouldn't serve Flügge lots because she was a woman, and she was the only woman at the Institute at that time in an engineering type position. So she had to serve her own tea. Then I guess Flügge saw things going down the tubes at Göttingen, and he went to Berlin in '38, and she came with him. And then when things got a little worse, they moved to Paris. And finally, in '44, they wrote to Timoshenko, who they knew. Timoshenko knew everybody. They wrote to Timoshenko and said, what about getting us out of here? So in '48, Timoshenko arranged for them to go to Stanford. But there was a problem. They had never had a woman as a professor at Stanford in engineering. And they said, we'll give Wilhelm a position, but we're not going to do it for her. And so they went there because times were so bad in '48. And Flügge Lotz, in many respects, was more famous than Flügge. And finally, Stanford had to admit that this person is really good, and she deserves to be a professor. But that didn't happen until 1961. So she was not permitted to be a professor for 13 years at Stanford, although she was an internationally known person. So I find those kind of things interesting. She was, by the way, the first woman professor in engineering at Stanford. That was 1961. It seems remarkable. Okay. Next theorem follows pretty much the same lines. One more time, the virtual work theorem. And this time, though, he's doing it with the strains. And he has a dissipation term, if you like to call it that, on the next slide, a thing called capital D. He didn't really have to put that in, it all just falls out. And he ends up with a comparable expression. And if you look at the last equation on that page, he ends up with this M, and it's a multiplier. And you got the same problem here that you had before. Therefore, the what do you call sigma star this time can't exceed the yield point, and therefore M has to be greater than 0, and the applied load has to be, that you've guessed, has to be greater than the actual load. So that's a much simpler proof to follow. What I want to do now is expand slightly on what I've already said about the use of limit analysis with structures. And I really just want to call to your attention the book Plastic Analysis of Structures by Phil Hodge. This is the same Hodge of Prager and Hodge. It's a McGraw-Hill book, and you can see that it was published in 1959, whereas the Prager and Hodge book was published in 1951. So this was some years later, and you can see that that Hodge by this time was at Illinois Institute of Technology, where he's spent a lot of time, but I've mentioned before that he liked to hop around, so he was never in one place too long. Anyhow, in this book, he really expands on what I would call the civil engineering outlook concerning limit analysis. Although in the book he covers things like beams, frames, plates, and shells. And as always with the stuff Hodge does, it's very innovative, correct, and in this book there's more than in Prager and Hodge, there's some practical discussion of the answers. The civil engineering community would be more attracted to this book than to Prager and Hodge because it deals very heavily with structures, and that the use of limit analysis in structures was pretty active. Maybe still be, for all I know. And in fact, that's where Paul Simons did most of his work, was in structures. And this book, in the beginning at least, capitalizes on this notion of a finite number of collapse modes of these frames, and how to go about it. And there's some special mathematical techniques that he covers. So in that sense, it's conceptually different from Prager and Hodge, but it's exactly the same theory. So I don't want to say any more about it than that, but if you're interested in these sort of things, Hodge's book could certainly be recommended as a very good, and for that time, very comprehensive coverage. On the next slide, I've got a funny looking sort of cloud with some arrows sticking out of it and so on. This is an attempt, really, and primarily by Dan Drucker, who I just mentioned. It's an attempt to get a more general relationship between the yield surface and the plastic strain increment that occurs when the stress reaches the yield surface. And this more or less characterizes a lot of the things that Drucker did. It's interesting that he was a student of Riemann Mendlin, who everyone thinks of as a theoretical sort of a fellow mainly in elasticity. He was at Columbia, and Drucker got his PhD from Columbia. But the interesting thing to me is that both these fellows, who are thought of as very theoretical, well, Mendlin's dead now, and so is Drucker, but they were thought of as very theoretical people. Drucker's thesis was on three-dimensional photoelasticity, an experimental thesis. So he got around a lot. He also spent some time at IIT, and I think at that time he was heavily involved with the Armour Research Institute, which is used to be the research arm of IIT. So professors, you could be a professor at IIT and sort of have your finger in over at Armour, and Drucker participated in that. Well, anyway, he was trying to tie things down a little bit as to what you might expect, and he on this work, he was interested in his notion of stability of a material. And it's true that not all materials are stable materials. And he restricted himself really to plastic behavior and the determination of whether the material was stable. The main effort that he has is sort of like an energy method. And he imagines that he has a yield surface, and you can see that's the cloud on the left. There's a zero place for the stresses, and there's a little sigma vector there. This could be the pi plane. It could be any kind of yield surface that you want to think about. And so what's happened here is that the stress has reached the current yield surface. So he doesn't care if it's work hardening. He just lets it go. But he wants to say, but I want the material to be stable. So he has two criteria. One that was referred to usually as stability in the large. And in a way this looks obvious, but I'll point out that it's maybe not as obvious as it looks. In the stability in the large, what you're saying is that if you think of these stresses as vectors, that the dot product between the stress that's being applied and the plastic strain that results has to be greater than 0. And the second is that I've written it in a strange way. I say that d sigma dotted with d epsilon has to be greater than 0. Well, you may wonder a little bit about this, but they look like after you've been with them as long as I've been, it's pretty obvious what's going on. The first statement says that you have to do positive work on the material in order to advance the stress beyond the yield point. Now, there's some materials that just don't fit into that. For example, if you take something like a sand or a soil that compacts. If you've ever noticed this, when you take things that crumble, that they start to break up in areas all over the place. They don't shear uniformly when you apply a shear stress. And in particular with soils, you find that that you'll be able to shear it, but the motion occurs over a single sort of a slip plane. And it's that sort of thing that you need to think of when you're trying to study something like a landslide. These materials have the characteristic that when they're in a compacted state and you shear them, the volume increases. And that that'd be a local change in density, and as the density gets to be less, the stress that it takes to deform the material plastically goes with the density. That is, a dense material is harder to get started moving than a less dense material. So what would happen when you come up to this surface now is that d sigma won't go out. It comes back in because the yield surface collapses on you. So you could hardly expect to analyze this using equations that are appropriate for a stable material, according to Drucker's sometimes called hypothesis. The second stability in the small condition can be, as it's depicted here. You can also do this in a different way. You see it in a different way sometimes in books, that instead of just having sigma, the way it's drawn here, you can have two steps. I go from the origin O out to some point not on the line that is shown there with sigma, and then I can stop there. I'm still inside the yield surface, so it's all elastic so far. And then I can put a second load on that goes up, gets to P eventually. And you can write this second condition as saying that last step of loading, dotted with the plastic increment, is greater than 0. So that's a different way of looking at it, but I'll be mentioning something like that toward the end of all these lectures. Anyhow, what this second condition says is if that d sigma dotted with d epsilon has to be positive, then it's the case that my d sigma could take any direction when I get to a point P. I can impose the stresses in any way I want, and every time I've got to have the growth in the plastic, the growth in the yield surface has to have a positive dot product. What that says is that this d epsilon p has to be normal to the yield surface. Now, Hill, in his book, built in von Mises and the Levi-Mises equations. And so you have a circular yield surface with a radial increment in plastic strain. So everything in Hill satisfies Drucker's stability condition. This normality condition is not observed by everyone. So when someone is using a theory and they want to say, I've used normality, sometimes that's what they say. And sometimes they say, I'm using this yield surface with the associated flow rule. That means the normality condition. There's also, if you fiddle around with this a little bit, using the two-step load to get to the point P, you can show that the yield surface has to be convex, because otherwise you would violate these conditions. So if you think about that, all the yield surfaces you're apt to find are going to be convex. All the popular ones definitely are. So this is really considered to be a significant contribution to plasticity. And it's interesting to see how different people think. And Drucker was really the one that got off on this and convinced everybody that that's the way things were. Okay, I want to go on now to yet another subject. And this is a book that Prager wrote in 1959. So it's the same year as Hodge's book, but it's certainly not he's not a competitor in this case. He's doing something completely different. And Prager got onto this notion, which was already around, that if I have a yield surface and I start to increase my stress and my stress gets to the yield surface, we've talked about how the yield surface changes as the load progresses so that the stress point is outside of the original yield surface. And what Prager and Hodge did, what Hill does, is they use isotropic hardening. That's already been mentioned. But Prager wrote a whole book on kinematic hardening. And in kinematic hardening, you don't let the yield surface expand, you drag it around. And that's what this book is dedicated to. And this is a good source to understand these kind of materials. A number of people have gotten hooked on this sort of stuff and written a lot of papers. But this is the best fundamental understanding that I'm aware of. So I have taken just a picture out of it to try to give a little bit of a notion of what's in the book. I don't want to get into this because it's almost never used. But like a lot of these things, it's really good to know, even though you don't use it. Prager credits Coiter with advancing this idea of kinematic hardening. And Coiter was, let's see, his first name was Warner. His second name was Tjardus, which I can't pronounce. Anyway, he was around from 1914 to 1997. His main interest, well, he was heavily mathematically oriented, but his main interest was elastic stability. And he got into this business about the kinematic hardening later on. Then there was a fellow named Moreau. I don't know how to pronounce his name really. It's M-R-O-Z with a funny mark over the Z. And he picked up on this and wrote a series of papers. But I've never been convinced that he had it just right, but you'll see his name in the literature. Anyway, Prager starts out by trying to give you some feeling for what this kinematic hardening is all about. So we have these cute little pictures. I want to talk about those too. You see this all the time. Someone wants to model an elastic material. So they draw a picture of a little spring like this, figure 1-1 on the slide. And I guess that's okay. You have this notion in your mind that you pull on it, it stretches, you let go, it comes back. Then there's a notion of a plastic element, and that's like a block that weighs something sitting on a frictional surface. So you've got to pull with a certain force before it moves, and then if you use Coulomb friction, then you will have what is in the second picture, figure 1 and 2. Then if you have elastic plastic, you get a picture like the one where he's combined the spring and the block. And the stress-strain curve is shown over on the right. It's elastic until you overcome the friction, and then it becomes plastic. Well, I don't know how much it helps, but he's got a picture to portray the sort of material that he's looking at. It's a one-dimensional picture. I'm sorry, a one-dimensional model for the material. And he's got this oblong container called a slotted plate in his book. And that slotted plate slides in a frictionless guide, and those are the horizontal lines bounding the slotted plate. Then inside the slotted plate, he's got a pin. And the pin just moves back and forth in the slotted plate. And what he's saying is that if I start from where he's showing the stress is 0 at the bottom there, that you go through an elastic region until the pin hits the slotted plate, and then you then move the slotted plate, and when you move the slotted plate, you move its whole length. So when you try to bring the pin back, you can come back twice as far as you went from the 0 stress, but that's all. So I don't find this picture overwhelmingly clear, but it's okay. If you're better off if you read the explanation in his book, I guess. The reason I put this in, I mean, as well as showing what Prandtl was up to, is in 1961, Drucker wrote a paper, which I've always thought should have been famous, and I seem to be the only one that remembers the paper. But Drucker was talking about figures like this, And in particular, a fellow named Ziegler had used some figures like this to make some arguments in a paper. And really the comments by Drucker showed up in a discussion of Ziegler's paper. It was a meeting in Haifa where this took place. And what Drucker was pointing out is that there's a subtle implication when you run around drawing pictures like this. And that is that you are depicting somehow the material. And the implicit in the way you think about it is the way you would think about steel. I can take a little piece of steel, I can measure Young's modulus, Poisson's ratio, get the elastic properties. I can measure yield point, get the plastic properties. I can take a sample twice as big, and the properties don't change. Now, if I was imagining this material as being made up of a lot of little elements, like these sketches show, then they should have the property that if I were to make an array of them, so suppose I took one of these and stacked them next to each other and then put another stack up here and another stack up here. If I take that model and I go to find the stress-strain relations for that model, they should be the same, looking at stress and strain. They should be the same as the individual element. And you get into some trouble when you have, excuse me, when you have a nonlinear element, because it doesn't come out this way automatically. Now, a person that pays attention to what they're doing and has a good physical feel probably won't get into this trouble. For example, I mean, the models that you could draw for Hill's material, for Prager and Hodge, for this book of Prager's, they all pass the test. But there is a test there, and you, I think, would be inclined to say, well, if this doesn't work, if I don't get the same stress-strain relations when I have a bunch of these elements, then I really want to be very careful about accepting that as a valid model of the material. The other way around is, and I only know of one paper where this has been done, where the properties were left a little vague, then all the elements were put together, and the conditions were worked out to find out what characteristics these properties had to have in order to meet this condition, where when you put a bunch of them together, the stress-strain curve doesn't change. And that really impressed me, but I guess I was just about all alone on that. But I thought I'd mention it because it's related to plasticity. And the place where I have tempted to make a fuss, but I never had the energy, was in the representation, usually by chemical engineers, to describe plastics, because they get very caught up in the molecular characteristics of the molecular chains within the material, and they're getting involved in that and sometimes chemistry. And I don't believe they ever think about this notion of Drucker's, about making sure that the stress-strain equations are independent of the size of the sample. So I thought that would be a good thing to throw in. Well, Prager works on the next slide. I'm just going to talk a little bit about this. He works a pretty simple problem. It's one that plasticians always seem to love to work on, including Hill. Combined tension and torsion of a thin-walled tube. The reason anybody would do that is because it really is possible to run fairly intricate experiments on these. And thin-walled might mean a d over t of 20 to one person and 50 to somebody else, but
Prager works out a little problem and shows it, and this little figure he has is his yield surface, and it's moving around, so he's keeping a constant, he's using a Mises condition. He's using non-work hardening, so he's got a circle, and he says it's incompressible both in elastic and plastic strains. And he writes down then the governing equations, and he uses, as he should, the normality condition in here. So he's using exactly what Hill uses. The only difference is his yield surface is drifting around. And as the stress moves, the yield surface has to move over. And it has to move so that it's the normal at the point where the stress hits the yield surface has to give the direction for the motion. And there's a little discussion in this. He's showing how the surface moved over. Then he comes up with something, and this is the sort of thing that I was mentioning this man, Morose, if I'm pronouncing it right, was doing, or maybe still is doing. And really, what they're doing is they're saying, I got a whole mess of these circles. I don't just have one. And let's say I take this material and I anneal it. Then I could hypothesize that in my, you notice we have a strain space in that figure above. In the strain space, if I draw my yield surfaces, they'd all be concentric. Then I start to push, and as I push, I drag the first little circle because I hit it first. And then I hit the next one, and the next one, and the next one. And you can actually then, by taking an infinity of these, you can match any old curve you want. One of the interesting parts of that is that if you do that, you can show that Massing's hypothesis, remember that about taking the loading curve, flipping it twice and doubling the size, and then tagging that on to where you stop loading, that was Massing's hypothesis. And this material satisfies that. And that's a good thing, I think, particularly if you're interested in single crystals, and a lot of people are. Okay, then this last, on the next page, he works out something that it's sort of useful. It gives some detail about how you might actually go about working out something for an incremental loading. And what he's got here is it's a two-dimensional problem, and he's got a sigma 1 and a sigma 2 as principal stresses. And now he's talking about loading it to yield and what would happen. So he starts out writing things we already know about: the von Mises condition, the plastic flow law, that's this normality stuff. And then he writes these two equations, and he solves them for the stresses. So you get these two equations that involve the stresses equal some combination of the plastic strain increments. Put those into the yield condition, and you've got this lambda, the famous lambda that we always had, Hill and Prager, with all of them. And he uses the yield condition to eliminate the lambda, and he gets these expressions for sigma 1, sigma 2, and plastic work in terms of those plastic strain increments. Now, that's sort of the essence of how you work problems in his book. And aside from the cute result that it satisfies Massing's hypothesis, So it has a Bauschinger effect, although it may not be exactly correct. At least it's got it. And I think that's all I want to say about Prager's book. I consider it a very good book. I consider it a real contribution to plasticity. But it's a complication in working problems that has never caught on. And so you may never see this used in your entire life.